To understand why anyone would muffle alarms at Yellowstone, we need to go back, before dashboards and press briefings, to the engine under our feet and the rhythm it used to keep. The ancient engine underfoot. Start with a torch that never moves. The North American plate slides, but the hotspot stays, burning a dotted line across states and time. That's the Yellowstone hotspot. Mantle heat welling up, softening crust, feeding a system that breathes in centuries and exhales in moments. Geology books sketch it as arrows and blobs. On the ground, it became 3 stories written in ash and panic. 2 million and change years ago, the Huckleberry Ridge event ripped open the land. Not a cone exploding, but a continent exhaling. Pyroclastic flows racing faster than a car, ash fanning across what would become the Midwest, the sky turning a steel gray that midday sun couldn't punch through. People weren't there to tell it, but if they had been, the first chapter would have been noise. A low, endless freight train roar swallowing valleys. Then the wind would have taken over, sewing glass needles into lungs, making agriculture a memory. The caldera collapsed, a floor dropping, a roof falling in on itself, and the map changed. A million years later, a smaller flash. Mesa Falls. Smaller like a hurricane versus a superstorm. Still enough to sandblast forests and make rivers forget their beds. Another caldera scar, another chapter in a hotspot's long handwriting. The pauses between weren't quiet. Rhyolite lavas crept and froze. New geothermal basins boiled to the surface. Groundwater learned new routes through fractured rock. The system rested the way a boxer rests, standing, breathing, never fully still. Then came Lava Creek, about 631,000 years ago, the eruption everyone points to when they talk about the supervolcano. Its ash blanket shows up in drill cores from coast to coast, a thin gray line that geologists pull out with tweezers and a grin, because it's time travel in a smear. That line is a clock tick. It says, this place can build pressure quietly for a very long time and then spend it all at once. Meanwhile, under our later boots and cameras, the plumbing kept evolving. A lower reservoir, deeper, hotter, buoying less viscous melt, feeds an upper, cooler, crystal-rich body, more a mush than a lake of magma. Between them, cracks and sills and dikes, the capillaries that let heat and gas and melt move. When the valves are partly open, we get geysers, center terraces, sulfur breath on a windy day. When a valve sticks and a seal fails, we get hydrothermal blasts, steam-driven explosions that snap trees like matchsticks and leave craters where tourists took photos last summer. Ask anyone who's hiked before dawn with a field crew. The ancient engine isn't abstract. There's the crunch of brittle center under your boots, the hiss from a vent that wasn't there last week, the sudden metallic taste when wind swings and you realize the gas has changed. More CO2, a sting like rotten eggs turning up in the mix. Someone checks a handheld meter and says, "We don't linger here." They don't have to say why. Out beyond the boardwalks, the record in rock is patient and blunt. In a lab, a thin core spins under a microscope, and a grad student sees shards of volcanic glass, bubbles frozen mid-escape. The ash layers stack like lines of code. They say long dormancy punctuated by fast events. They also say dormancy is not sleep. It's storage, it's assembly, it's heat moving into place. A ranger remembers his first steam blast at Norris. No warning, just a hard call from the ground and a column of gray-white punching up. Nobody got hurt that day. The crater was the size of a pickup. It felt like the system clearing its throat. Later, he learned there's a pattern. Pressure builds in the shallow plumbing. Water flashes to steam. Rock breaks. Small doesn't mean trivial. It means the lid still holds. Now take the map and zoom out to farmland, to grain routes, to power lines strung across plains. The hotspot's plumbing matters because we live downwind and downstream of it. Ash isn't dust, it's microscopic glass. Put enough of it in jet engines and they stall. Put a few millimeters on high voltage insulators in damp air and you get flashovers and blackouts. Put a gray film on a wheat field at the wrong part of the season and yields drop. That's not apocalypse talk, it's logistics. But the past sets more than stakes, it sets expectations. The old rhythm that creeps into public conversation goes like this. 3 huge eruptions with hundreds of thousands of years between them, so the clock must be slow. You can almost hear the comfort in that. The engine's big cycles look like they give us room to breathe. Here's the catch we'll keep coming back to. Those big eruptions were the last pages of long chapters. Between them, the engine kept moving heat, flipping valves, sealing and unsealing pathways. The pauses held action that didn't leave postcard volcanoes, but did leave signals. And when you listen to those signals with today's instruments, GPS pins, satellites feeling the ground rise, seismometers counting the tiniest pops, the rhythm doesn't land where the old clock says it should. We carry that thought forward because it decides what we do with alarms. The ancient engine taught us how it spends pressure. Our gauges tell us how it might be saving it now. The official clock and its blind spots. The old rhythm shows up in headlines as a number, overdue by 70,000 years. It sounds precise, like a train schedule. It comes from averaging 3 big eruptions and subtracting the time since the last one. Simple math, wrong metaphor. Volcanoes don't count evenly spaced beats. They hoard heat and change plumbing until something tips. Even the agencies push back on that myth. They'll say recurrence intervals are not timers. They're right. In fact, with only 3 data points, the average is statistically meaningless for prediction. Some popular retellings say 70,000 years overdue. Others say about 100,000 years to go. Both miss the point. There is no countdown clock. But the comfort lingers because a slow clock is easier to live with than a twitchy one. So the official clock leans on what can be measured and averaged. The monitoring pillars are the pendulum. GPS monuments cemented into bedrock, tracking millimeters of uplift or subsidence. INSAR satellites watching the caldera breathe from orbit, stacking images into color bands that reveal bulges and sags. Seismometers listening for microquakes most people never feel, the tiny breaks and slips as fluids and rock adjust. Gas stations sniffing CO2, helium ratios, the sulfur that betrays fresh magma if it reaches the surface. Rangers and geologists logging hydrothermal behavior, pools clearing or clouding, vents migrating, geysers changing intervals. The models that sit behind those instruments were built in an era of patience. They weight long repose times heavily and assume recharge that behaves like a slow IV drip. If the ground is rising a few centimeters a year and the gas looks mostly like old water boiling, the model calls it background variability. If swarms come and go without strong low-frequency events, the model nods. Normal for a restless hydrothermal system. The public line follows the model. No eruption imminent, variability expected. But there's a blind spot baked into that comfort. It shows up in the rocks, not the reports. Magma at Yellowstone isn't a single vat. It's a spectrum from crystal-rich mush to hotter, more mobile melt. The difference between a quiet mush and an eruptible pocket can be a small thermal push or a pressure change that melts the ice between crystals. Crystal clocks, zircon and feldspar, capture that. They record episodes when heat surged and mush flipped to melt in decades to centuries. Not glacial time, human time. Comparable decadal scale remobilization has been inferred at other caldera systems, which is why averages don't forecast behavior here. Meanwhile, models that treat melt as a single velocity fluid miss what happens when different domains couple. A dike injection at depth can connect compartments and fluids, CO2-rich first, outrun the melt, pressurizing shallower zones, changing seismic patterns and gas without obvious sulfur. The hydrothermal system acts like a shock absorber until it doesn't. The official pendulum watches averages. The system moves in bursts. A scientist told me how that plays at a conference. She had a slide. GPS curves from 2004 to 2001, then the later pulses with short, sharp uplift bursts circled. Her note under the figure said, rate changes incompatible with pure hydrothermal forcing. The night before the talk, during a prep call, a senior voice suggested a softer phrase, consistent with known variability. She changed it. Later, over coffee, she shrugged. Words matter, she said. So do grants. She didn't sound bitter, just tired. What nobody knew in real time during those pulses was how patchy the ground moved. The caldera center rising while the edges sagged, then flipping, dome versus basin, asynchronous, like a heart with a skipped beat. The model flagged it as expected, breathing. But there was one detail that stuck. The short, sharp bursts. They arrived faster than seasonal snowmelt artifacts, too broad to be a single geyser basin pressurizing. They suggested intrusions, thin sheets of magma or hot fluids wedging in then
stalling. If you live anywhere downwind, Denver, Billings, Rapid City, Omaha, even Chicago on the wrong week of wind, these patterns aren't trivia. They're the early moves that, if they cascade, decide whether planes fly, grid gear stays clean, and food prices don't jump next season. Here's where the blind spot tightens. The sulfur puzzle becomes an excuse. No SO2, no fresh magma, the line goes. Except sulfur scrubs easily in a wet, capped system. It dissolves into water and binds in rock before it sees daylight. CO2 and helium ratios are harder to hide, and they started whispering mantle fingerprints in expanding degassing fields. The official clock, tuned to sulfur, missed the new fuel signal. Another meeting, another memo. An interagency call wrestled with a word: unrest or variability. Unrest trips thresholds. Tourism boards get antsy. Emergency managers ask for money. Variability maintains calm and keeps the phones quiet. The compromise was a bland paragraph and a promise of ongoing review. In the same hour, a flight to sample gases over a northern basin was postponed for internal quality control. The pilot put a question mark next to the date on his log and didn't erase it for 3 months. From a distance, all this looks like caution. Up close, it feels like drift. The clock is slow until it's not, and language keeps it slow. The instruments are good, the people are careful, but the framework lags the physics. Multi-velocity magma, mush-to-melt switches, rapid mobilization. Those aren't fringe ideas, they're the current literature. The official pendulum hasn't caught up. While models sleep, the ground started moving differently. And in the next beat, something else began to speak. Gases rising through cracks that didn't exist a decade ago, hinting at plumbing the old clock never timed. The uplift that wouldn't behave. Start with a curve that doesn't care about explanations. In late 2004, the caldera floor began to rise. Broad, steady, undeniable. GPS pins at White Lake and Sour Creek drifted upward like someone was cranking a hidden jack. Over the next years, through 2009, the whole bowl lifted tens of centimeters. The official line called it caldera breathing. Inside field trucks, the word was simpler. It's moving. If that pulse had been the whole story, the model might have survived untouched. But the ground didn't keep one rhythm. After the big rise, it eased, then subsided, then rose again. Shorter pulses nested inside the longer trend. The strange part wasn't just up versus down, it was where. The two main domes, Mallard Lake on the southwest, Sour Creek on the northeast, took turns bulging while the other side. 1 month, the northeast swelled like a slow tide while the southwest flattened. Then the pattern flipped. It looked less like a chest breathing and more like plates shifting under a tablecloth. That asymmetry matters. A hydrothermal system can pressurize, sure, but it tends to show its hand locally. Basins puffing, vents hissing, a boardwalk buckling here and there. These were basin-scale moves, tens of kilometers across, too broad for a single steam field, too asynchronous for a uniform aquifer cycle. They pointed to intrusions, thin tongues of hot material wedging into mush zones, rather than just water flashing to steam. Meanwhile, satellites watching from orbit painted the same odd picture in color bands. Interferograms stacked over months showed concentric rings that didn't share centers. One bulge here, a sag there, then a new lobe swelling off-axis like a bruise migrating under skin. The timing didn't line up cleanly with snowmelt or lake level changes. Analysts tried to clip out seasonal noise. The bursts remained. Those short, sharp bursts kept coming back. A GPS monument would tick upward a few millimeters in days, pause, then slide a hair, repeat. Too fast for deep crustal flexure, too coherent to blame on one frozen sensor. In meeting rooms, the phrase episodic intrusion started to appear in the margins. Not a continuous pressurization, but pulses. Dikes or sills squeezing in, stalling, degassing, maybe cooling, then another pulse. The hydrothermal hypothesis fought back. Yellowstone's shallow plumbing can seize and relax in days, that's true. But if steam alone were the driver, you'd expect stronger synchronized signals in the nearest geyser basins. Sudden changes in intervals, water chemistry flipping, new blowouts aligned with the deformation lobes. Some of that showed up, but not with the right cadence. The ground seemed to get the memo before the basins did. A field micro-story. A summer tech named Lila babysat a GPS site near the Sour Creek Dome. She hiked in every week with a toolkit and a thermos, cleared snow from the solar panels in spring, shooed bison in July. In September, her receiver logged a 2-day jump, 5 millimeters up, 1 east, clean, no multipath. She sent a note. The reply was a template about seasonal effects. She taped the plot inside her trailer. Anyway, when the same 2-day hop appeared at a station 20 kilometers away, a month later, she circled both in red and wrote, "Buddy system" on the printout. It became a quiet joke until it didn't feel like one. Dome versus basin dynamics tell you something else. The system isn't a single balloon. It's a stack of cushions with leaks and clamps. When the upper reservoir takes a pulse of heat or gas, it can swell where the mush is primed. Warmer, wetter, crystals less interlocked. Another patch might sag as fluids escape along a fault. Pressure bled off before it can lift rock. You end up with asynchronous teeter-totters instead of a tidy inhale-exhale. Seismology added texture. During some uplifts, small swarms trace lines at the edges of the domes, little brittle pops sketching possible intrusions, then going quiet. Low-frequency tremor, the kind that hints at fluid movement, flickered more under Norris and West Thumb than directly above the biggest bulges, as if the pressure wave was rerouting through old fractures. If magma was a messenger, hydrothermal zones were its gossip chain. Through all this, one argument kept resurfacing. Rate matters. A centimeter a year is one thing, a centimeter in a week is another. The first suggests deep, slow forcing. The second hints at something mobile. Rate changes, accelerations, and sharp stops are how you spot a valve being opened or a seal wedging in. The official summaries liked cumulative maps. People in the field watched derivatives, the slope of the slope. And then there's the silence of sulfur. During several uplift spells, SO2 at the surface stayed low. That fed the steam-only camp. But look at CO2 flux surveys laid across meadows over those same months. Patches of high emissions spreading, tree roots suffocating in new dead zones. Look at helium isotopes drifting slightly toward mantle signatures. Those signals arrive early and travel far. Sulfur gets scrubbed, carbon slips through. What this all implies is uncomfortable and practical. If the deformation is driven, even partly, by episodic intrusions coupling to a patchy mush, then the system's response time isn't glacial. It's immediate. A thin dike can move in days. A shallow seal can fail in an afternoon. The difference between we'll know centuries ahead and we'll know after lunch is in the rates, the asynchrony, and the coupling we see on these curves. Ground moves slow, people say. True, until it doesn't. In Yellowstone, the ground started moving like a conversation. Call and response across domes, interrupted sentences, sudden emphasis. That's not how a clock breathes. It's how a system negotiates new plumbing under pressure. Gas whispers from below. If the ground is the body language, the gases are the breath. Quiet, warm, and full of clues. Start with carbon. CO2 seeps out of Yellowstone year-round, but the pattern has been changing. Survey teams laying plastic chambers over meadow soils kept finding bigger hotspots. Patches that weren't there on older maps, where meters tick up and tree roots brown from strangled oxygen. On cool mornings, you can see it in the way fog hangs odd in low spots, thicker than it should be. A ranger calls it ghost air. The chemistry calls it an expanding, diffuse, degassing field. The ratios matter more than the totals. Helium has flavors. Most of what we breathe is crustal, but a small share, helium-3, carries a mantle signature. When the 3/4 ratio nudges upward, even a little, it's a fingerprint of deeper input. In several basins, those ratios bent toward mantle values at the same time CO2 flux grew. That pairing is hard to blame on boiling old groundwater. It says the system isn't just exhaling yesterday's steam. Something fresh is pushing from below. Then there's sulfur's quiet. People expect to smell rotten eggs if magma climbs. In a dry, open system, you would. Yellowstone is neither. It's wet, fractured, and capped. SO2 dissolves into water, reacts into sulfate, gets trapped before it reaches the sky. So when the official line leans on no sulfur spike, they're trusting a break that's built to hold, until it doesn't. Meanwhile, carbon slips through early, faster, farther. If you want the early whisper, you listen for CO2 and helium, not the shout of sulfur. Micro-stories accumulate. A hydrologist sampling the fire hole noticed the river's dissolved inorganic carbon jumping a few percent above its usual swing, right as an upstream meadow's CO2 flux map added new red pixels. The same week, a cottonwood stand at the edge of that meadow yellowed from the bottom up, a classic suffocation pattern. In her field book, she wrote 2 words underlined twice: fresh input. Another, a pilot with a nose for thermals flies a fixed-wing pattern over West Thumb to chase down a routine gas transect. 2 hours before takeoff, the run is paused for internal review. It's not the first time. He logs the cancellation, adds a question mark, and goes home. 3 weeks later, the same. Transect gets a green light, but by then the wind patterns have shifted and the lake's thermal skin has cooled. The data are clean. They're also late. Gas doesn't move alone. It drags water chemistry along. In the Madison River, A summer profile picks up slight increases in bicarbonate and a trace of chloride where a cold tributary should have diluted everything. Not a headline, but a nudge. The lab report's footnote mentions isotopes trending toward magmatic CO2. Small but coherent, the analyst writes. That phrase keeps showing up. Meanwhile, trees tell their own version. At Norris and near the North Rim, foresters flag new mortality patches, irregular ovals where conifers browned in clumps. Soil probes beneath them read high CO2. The pattern spread downslope over a couple seasons, not with beetle galleries or drought stress, but with invisible gas pooling in hollows on still nights. The park's botanist filed it as physiological stress likely due to soil gas. The volcanologist filed the map. The absence of sulfur remains the puzzle that comforts. It shouldn't. At Campi Flagre and Rabaul, similar wet caps muted SO2 until systems unzipped and the signal jumped from silence to scream. Yellowstone's cap is broader and colder, a champion sulfur scrubber. If you're waiting on that scent to declare fresh magma, you'll be late by definition. Then there's a detail most visitors miss: bubble size. In a few pools that used to simmer gently, bubbles grew fatter and fewer, classic CO2-rich degassing. Boiling water makes chains of tiny, frantic pearls. Carbon makes heavy beads that pop with a soft thud. A tech at West Thumb filmed it, slow motion, and laughed in the lab. "It's like the system switched soda brands," she said. Her supervisor nodded, then added the clip to a training deck on gas signatures. All these threads, ratios, rivers, roots, bubbles, point in the same direction. Renewed input from below, not just old water finding a new crack. The timeline attached to that is the part that bites gases outrun magma. CO2 can be the first postcard from an intrusion we won't see on a satellite for months. That's why canceled flights and delayed field runs matter. The early signal is perishable. Impact lands quietly. The more domains that light up, meadows, river chemistry, isotope ratios, the tighter the plumbing feels. Pressure couples faster. Hydrothermal caps stiffen, then creak. Valves that held for decades start to chatter. If gas says new fuel, it's telling you the engine's throttle just opened a notch. And if that's true, the next voice that rises won't be a whisper. It will be the map of tiny earthquakes learning new routes through rock.